In the previous module, we introduced how the different types of information are represented in the computer. In this module, we will discuss how these representations are actually implemented in the hardware. In particular, we will give a brief introduction on how electronic circuits are used to represent and process information in a computer and to control the computer itself. Now, electric signals can be used to represent information in two ways. Digital system, which represents information in a discrete form, where a value is represented by high and low voltages, forming the binary digits of the value. And number two, an analog system, which represents information in a continuous form, like a value is represented by a voltage proportional to the value. After this module, you should be able to discuss how information are implemented in a hardware, simplify a logic expression, and convert logic expressions to logic circuits and vice versa. In different logic levels, when a bit is represented by a voltage in a wire, there is a range of voltages which is acceptable for one state or logic level and another. It is non-overlapping range of voltages which is acceptable for the other. If the voltage falls outside both ranges, the logic level is undefined. Typically, the low logic level is from 0 to 0.8 volts and a high logic level is from 2 volts to 5 volts. We have to remember that on different technologies, there are also different state representation. We remember our binary values. If it's 0, it's like low or off, and 1 is high or on. For a transistor logic, it is represented by this in volts for 0 and 1 for 2 to 5 volts. For fiber optics, we know that for 0, that means light is off, and for 1, light is on. For a dynamic memory, it will be having the capacitors discharged for 0 and 1, that means capacitor is charged. For a magnetic tape or disk, the state representation of 0 means no flux reversal, and for 1 it is flux reversal. Moving on, we have combinational logic. When we say combinational, if a circuit has output which depend only on its inputs and not on any information stored within the circuit itself. We also have the term logic gate. This is an electronic device which performs logical manipulations on one or more logic levels or logic variables. Now, this logic gate is a combinational logic elements, which means these elements are the ones that accept inputs, combine them depending on the logical manipulations needed, and produce an output immediately after 10 nanoseconds in typical technologies. So what are these types of logic gates? We have 4 basic: inverter, an AND gate, an OR gate, and an exclusive OR gate. When we say inverter, this is a device which changes a low logic level to a high level and vice versa. An AND gate, this is a 2-input device with one input which is only high when both inputs are high. The OR gate is also another 2-input device with one output which is high if either or both of the inputs are high. An exclusive OR gate, this is a 2-input device with one output which is high if either input is high but not both. So, when we talk about binary logic, this consists of binary variables and a set of logical operations. The variables are designated by letters of the alphabet, any letters in the alphabet. with each variable having two or only two distinct possible values, 1 and 0. So for an AND gate, this operation is represented by a dot or by the absence of an operator. We say like multiplication. So for example, x dot y is equal to z, or this x y equals to z is read as x and y is equal to z. So the logical operation AND is interpreted to mean that z is equal to 1 if and only if the values of x and y are 1. Otherwise, whatever is the value of x and y, the output is 0. For OR operation, this is represented by a plus sign. When we see a plus sign, it's like we are thinking of addition. So we have example x plus y equals z. This is read as x or y is equal to z, meaning z is only 1 if x is equal to 1 or y is equal to 1, or if both x is equal to 1 and y is equal to 1. Then the rest is 0. For the NOT operation, this operation is represented by a prime or an over bar. So we say, example, x prime is equal to z, or x bar is equal to z, which is read as not x is equal to z, meaning that z is what x is not. For x or, this is represented by this symbol. For example, x prime y plus xy prime is equal to z. The exclusive OR operation means x or y but not both. Now we are going to look at the summary of the 4 logic gates. We have this symbol for our inverter or the NOT gate, or we say complement. So the truth table, that means if the input A is equal to 0, so NOT A is 1. Remember that there are only two values that our variable can hold. For an AND gate, if this is a two-input AND gate, let's say A and B, then 0, 0, A and 0, 0 and 0 is 0, 0 and 1 is 0, and 1, 0 is 0, and 1, 1 is 1. So, moving on, we have the OR gate. So, the truth table is this one. So, it gets a 1 output if either there is 1 in any of the inputs. And for exclusive OR, if both inputs are the same value, then you will get a 0 output. So we have an implementation example for combinational logic. Let's say the double complement of A denoted by A double bar. So that means A is the input, the variable here. Then this first bar is a NOT gate, so we put a NOT gate. But since it is a double, so the output here is A bar. Then it is put again in another inverter because A bar is inverted again. So that's why we have this circuit. Number 2, we have this. Let's say A or B and C. So we have B and C. We start with whatever is inside the parenthesis. So A and B here, B and C, the output is ORed with A. Then we get our output. So you will have your self-assessment question. You can draw and write the truth table for this one. There are 3 numbers. Please try to solve it on your own so you can practice. Now we have circuits for addition. This is under also in combinational circuits. This is a combinational circuit that performs the addition of 2 bits. We call it half adder. One that performs addition of 3 bits, 2 significant bits and the previous carry is called a full adder. So this one is the half adder. So it's 2 bits input. Then we have the carry for letter C and the sum for letter S. So let's say 0, Since it is an adder, so we add 0 plus 0, the sum is 0, and the carry is 0. 0 plus 1 is 1, the carry is 0. 1 plus 0, the sum is 0, the carry is 0. 1 plus 1 is equal to 2. So we have 0 carry 1. So now our answer is 2. So looking at our outputs, we have the sum and the carry. Now, when you're going to look at the sum column, it looks like an XOR truth table. And for the carry, this is an AND truth table. So you are expected to have one XOR for the sum, which is X, the inputs XY, and the carry is an AND gate. So now this is the whole circuit for your half adder, where your sum equation is X or Y, and the carry is X and Y. For full adder, this one is a 3-bit adder. So you have 3 bits X, Y, and Z for the inputs, and the carry and the sum for your outputs. So looking at this, it's an adder, so you're going to add this value. So like this one, this is 1 plus 0 plus 1 is 2. So sum is 0, carry 1. And 1 plus 1 plus 0, so 2, 0, sum, carry 1. And you also have 1 plus 1 plus 1 is 3. So this is 1, 1. Now a full adder adds 1 bit position with an integer to add an entire integer with n bits. We can use a parallel circuit or a serial circuit. A parallel circuit is more common, so it uses more circuitry but is faster. So looking at a full adder, it's just like a combination of one half adder and another half adder. You OR them, you get your carry equation. For this one is the sum of the full adder. So here we have another self-assessment question.